Hey everyone, and welcome back to The Explainer. Go ahead and grab your coffee, get comfortable, because today we are tackling a seriously high-stakes scenario, the kind of stuff that literally keeps developers up at night. I mean, we've all used databases, right? We all write SQL. But what actually happens under the hood when things go terribly wrong? Well, in this explainer, we're going to demystify database transactions once and for all and see exactly how databases manage to keep our data completely safe from the absolute chaos of power outages and random system crashes.
All right, let's just dive right into it. Picture this scenario. You're transferring $500 from your bank account to a friend's account. The bank's database kicks into gear. It deducts the $500 from your account, and then, right at that exact, precise millisecond, someone trips over a literal power cord in the data center. Boom. The server completely crashes before the system even has a chance to add that $500 to your friend's account. So the ultimate question here is, where did your money actually go? Did that $500 just vanish into the digital ether forever, or did it somehow miraculously make it to your friend? Well, the answer entirely relies on how databases use something called a transaction. Let's look at what that actually means in practice.
So the whole key to solving this missing money mystery really comes down to one single word: indivisible. A transaction is basically a group of database operations that are treated as one single unit of work. Think of it exactly like signing a legal contract. Either both parties sign the document and the whole thing becomes fully valid, or neither signature counts. There's absolutely no weird legal middle ground where one person is bound to the contract and the other isn't. The database works the exact same way. It guarantees that either all the operations succeed and get saved permanently, or none of them do. If something fails, it rolls everything back to the exact state it was in before the transaction even started. And to pull off this magic trick, databases rely on 4 core properties, famously known as ACID. So let's break those down.
First up is the A in ACID, which stands for Atomicity. And honestly, the absolute best way to picture this is to think of a perfectly working vending machine. A proper vending machine guarantees one of 2 outcomes, right? Either it drops your snack and takes your money, or it just returns your money entirely and keeps the snack. It is never, ever going to just eat your money without giving you the item. Well, that's Atomicity. All operations in a transaction succeed together, or they all roll back together. There is simply no such thing as partial success. So if step 3 of a 5-step process fails, bam, steps 1 and 2 are automatically undone. It's an all-or-nothing deal.
Next, we've got the C, consistency. In this case, I want you to think of the database as the ultimate referee. A transaction can only bring the database from one valid state to another valid state. It absolutely must respect all the defined rules. You know, things like foreign keys, unique constraints, or making sure an account balance doesn't suddenly drop below 0. Just like a super strict referee in a sports game, even if both players somehow agree to break a rule, the ref simply will not allow the play. If a transaction tries to violate any of these rules, the entire transaction is just rejected outright. It completely protects the structural integrity of your data. Moving right along to the I, which is isolation. So imagine hundreds of different transactions hitting the database at the exact same time. Isolation basically ensures that all these concurrent transactions execute as if they were running one at a time in a vacuum. Think of it kind of like a strict exam hall with private testing booths. Every single student, or in our case, transaction, works on their own paper in complete privacy. They literally cannot lean over and see what the other students are writing until all the exam papers are officially handed in. Any changes made by a transaction that's still in progress are completely 100% hidden from everyone else until that transaction officially commits.
And finally, we hit the D, durability. Basically, once a transaction successfully commits, its changes are permanent. We're talking carved in stone here, not written in sand. Even if the server crashes a microsecond after the commit is officially confirmed, that data is going to survive. Now, if you caught our very first explainer, you might remember we talked about the write-ahead log, or the wall. Well, durability is actually implemented using that exact wall. The commit record is safely written out to the physical disk before the database ever sends a success message back to your application. It's guaranteed.
So, look, ACID sounds amazing, right? It sounds like this impenetrable fortress for your data. But in the real world, well, implementation is actually incredibly tricky. While atomicity, consistency, and durability are fairly straightforward to pull off, isolation is notoriously difficult to implement efficiently. When you have thousands of queries running, perfectly isolating every single one of them just slows everything down to a crawl. So databases actually let us lower our isolation armor a bit just to speed things up. But when we do that, the armor cracks. Let's take a look at what actually leaks through.
Without that strict, perfect isolation, we run right into 3 classic database nightmares. Number 1 is the dirty read. Imagine reading a buddy's draft essay before they decide to publish it. You go ahead and quote it publicly, but then they decide, actually I'm going to delete the draft. Well, you've just shared data that never officially existed. In a database, this happens when transaction A reads uncommitted data from transaction B, and then B rolls back. Nightmare number 2 is the non-repeatable read. You're browsing an e-commerce site, you see a laptop for $1,000, you add it to your cart, but then when you go to check out in that exact same session, the price is suddenly $1,200. Someone else committed a change to that exact row while you were looking at it. And nightmare number 3, the phantom read. Imagine you're standing in a cinema, right? You count 10 empty seats. You look down at your notepad, look up 10 seconds later to count them again, and now there are only 8 seats. Someone else just inserted new bookings that matched your query. You're seeing phantom data literally appear or disappear mid-transaction, which, as you can guess, can cause absolute havoc for your application logic.
To kind of handle these nightmares, databases offer you a sliding scale of isolation levels. As you slide down from read uncommitted all the way to serializable, the data becomes much safer and you prevent more of those messy read problems. But here is the catch, and it's a big one. Higher isolation sacrifices speed. It requires a lot more locking, which means a lot lower concurrency. Now, here's a pretty wild fact that you're likely relying on every single day without even knowing it. Most databases do not default to total safety. For example, Postgres defaults to read committed. That means non-repeatable and phantom reads are still entirely possible in your app right now. Meanwhile, MySQL's InnoDB engine defaults one level safer to repeatable read. The big takeaway here is that you are constantly trading absolute correctness for performance, and relying blindly on database defaults means you're accepting a certain level of risk just to keep your applications running fast. So how does the database actually pull all this off under the hood? Well, let's connect this back to our previous explainer. Remember how we talked about databases storing data on disk using pages and organizing it all using B-trees for really fast lookups? We also introduced the write-ahead log, the wall. Well, that wall is literally the beating heart of atomicity and durability. Every single change is written to the wall first, and because writing sequentially to the wall is incredibly fast, it doesn't hold up your application. If the system crashes mid-transaction, the database wakes back up, looks at the wall and says, oh, wait, this transaction didn't have a commit record, let's discard those changes. If it did have a commit, it safely reapplies them to the pages and B-trees.
Okay, but what about isolation? Well, the old, kind of brutal way of doing things was just locking everything down. You know, if I'm reading a row, I lock it. You want to write to it? Too bad. You wait in line. This obviously creates massive traffic jams and completely kills your concurrency. But the modern, really elegant solution is something called MVCC, or multi-version concurrency control. So instead of locking, modern databases like Postgres and MySQL keep multiple versions of each row. When your transaction starts, it basically gets a consistent snapshot of the database at that exact microsecond. So if someone else is updating a row, they don't block you at all. You just read the older version of the row from your snapshot. Readers don't block writers and writers don't block readers. It's an absolute game changer for high throughput, letting thousands of users query the database simultaneously without stepping on each other's toes.
All right, let's bring this whole thing together. We're going to go back to that opening scenario, that $500 bank transfer where the power cord got tripped. Armed with all our new knowledge of ACID, the write-ahead log, and MVCC, let's run that exact same transfer in slow motion and see exactly how the database handles it.
Okay, step 1, we hit Begin. The database spins up a transaction context and timestamps it for our MVC snapshot. Step 2, we update Alice, deducting $500. This change gets written to the wall, and a new MVC version is created in memory. But remember our exam booth. Because of isolation, this new balance is entirely invisible to the rest of the world. Step 3, we update Bob, adding the $500. Same exact process here. Step 4, the database steps in as the referee. It checks the constraints. Did Alice's balance drop below 0? If yes, consistency steps in and forces an immediate rollback. If no, we're good to proceed. Step 5, we hit Commit. The success record is carved into stone by flushing it to the disk via the wall, guaranteeing durability. And it's only now that the new MVC versions become visible to everyone else. And Step 6, the crash recovery. If the server had crashed at Step 2, 3, or 4, basically any time before the commit, the database simply restarts, reads the wall, sees no commit record, and acts like the transaction literally never existed. Atomicity swoops in, saves the day, and your $500 is completely safe.
And there you have it, the absolute magic of database transactions. They're basically the invisible bodyguards of your data, just working tirelessly behind the scenes so we don't have to worry. But before we wrap up, I've got a challenge for you. Knowing everything we just discussed about trade-offs, do you actually know what isolation level your current application is running on?
Are you risking phantom reads for a bit of speed, or are you locking down your rows for absolute safety? Go check your codebase today. I promise you, the answer might actually surprise you. Thanks so much for joining me, and I'll see you in the next explainer.